Hi everyone. So in this video, I would like to go over my example molecule project. In several other videos, you've seen me make these different slides. Not really the slides, but the information that's presented on the slides, as we went through assignment 1 through 6. So I'm not going to focus on how I made the structures or anything like that here. If you need some information on that, you could go back and watch the previous videos for the different assignments. But here, I'm just going to focus on the presentation. Now, part of the presentation will be me actually giving the presentation, and then in some cases I'll give a little bit of commentary on how I'm giving the presentation. So in those cases, you wouldn't want to do that during your presentation. So for example, when we get to the molar mass slide, I may say something like, the molar mass is 237. I'm not going to talk about too much about how I calculated the molar mass, because that's a thing that everybody in an organic class is pretty aware of. You might not want to say that. You could just say I calculated the molar mass to be 237 or whatever it is. So that's basically how I'm going to try to do this. I'm going to try to keep it relatively concise and just go through these slides in a similar way that you might go through them if you're giving a presentation, with again that exception that sometimes I may give some commentary on how I'm doing it. All right, so for my organic molecule final project, I have 3-bromo hepta 5-enoic acid as shown here. So in the one of the first things that I did was I drew the expanded structural formula. I wanted to make sure that I showed 4 bonds to all the carbons. I also wanted to make sure that I showed the implicit hydrogens in the skeletal formula that I showed on the previous slide, and I made sure that I showed the lone pairs on all of the atoms other than carbon and hydrogen. The molar mass of my particular compound is 207.08 grams per mole. So one of the first things I had to do was identify the functional groups. So my molecule has kind of 3 functional groups. I have the carboxylic acid functional group at the end shown here. I have an alkyl halide, which is arguably a functional group shown here. And my molecule is also an alkene through this double bond here. Of course, it also has some alkane type structure as well, but I have not identified that as a functional group. My molecule does have 1 chiral carbon shown here. It's bonded to 4 different things: the bromine, the hydrogen, this group, and the carboxylic acid group. And I also have this double bond, which will play a role in stereochemistry because it could be E and Z or cis and trans. So in the next slide, I want to show you about the different stereoisomers. So first, I'd like to focus on the E or trans and Z or cis orientations here. So about the double bond, I can have them, the 2 carbon containing groups, on opposite sides in the E or trans configuration, or I can have them on the same side in the Z or cis configuration. And notice this one's Z and this one's Z, and this one's Z and this one's Z. As far as the chiral carbon goes, I have 2 possibilities. I can hold the smallest group to the back, hydrogen, and if I have bromine coming out and the other 2 in the plane as shown here, I get the R configuration. And if I switch those 2 things, so notice that I've switched the bromine and the hydrogen, I get the S configuration. So here I have 2 R's and 2 S's. And as you can see, there are 4 possibilities: E and R, Z and R, E and S, Z and S. So I have 4 possible stereoisomers as shown here. With hydrogen bonding with water, I had some carboxylic acid functional group, and the oxygens of the carboxylic acid can hydrogen bond with the hydrogen of water. And I also have an oxygen bonded to hydrogen, and this hydrogen can hydrogen bond with the oxygen of water. So this molecule is capable of hydrogen bonding with water, as shown here. For the polarity and solubility, okay, I identify this part of my molecule as mostly nonpolar. Now, of course, there's an argument to be made that a carbon-bromine bond is polar, and that's not incorrect. However, the most polar part of my molecule is this carboxylic acid group here. However, because my molecule contains 7 carbons, okay, and it's a carboxylic acid, it's pretty unlikely to be soluble in water. Generally speaking, we say that if a molecule contains 5 carbons or more and is a carboxylic acid, it will be insoluble in water. So I predict that this molecule is not actually soluble in water, even though it has a polar functional group and it can hydrogen bond with water, as shown in the previous slide. So for the incorrect separation scheme, so here I'd like to give just a little bit of commentary. So one way to approach the incorrect separation scheme and the incorrect mechanism is to break it into steps. So I've broken it into step 1, step 2, and step 3. And then I'm going to discuss in each step what the problem is for that specific step, as opposed to trying to go through all of the possibilities of what would happen if we did it correct, because I'm going to go through the correct separation scheme in just a minute. All right, so that's going to end my commentary, and now I'm going to go back to just doing this. So for my incorrect separation scheme, in the first step, we've added 6 molar sodium hydroxide. 6 molar sodium hydroxide would deprotonate this carboxylic acid and would not react at all with this amine. However, we've shown a deprotonated amine and an intact carboxylic acid, so this is obviously incorrect. In step 2, we've added lithium aluminum hydride, a common reducing agent, which has no place in a separation scheme, and I'm not going to even get into what it could do to this molecule because it's just an inappropriate thing to have in a separation scheme. In step 3, we have a carboxylic acid dissolved in ether, and we evaporate the ether. Fundamentally, this is correct. If we did have a carboxylic acid dissolved in ether and we evaporated the ether, we'd get back the solid carboxylic acid, and in the gas phase, we would have the ether. However, of course, there's a better way to do this, a correct way to do this, if you will. So one correct way to do this, there are others, is to start by adding ether and 5% sodium carbonate. The 5% sodium carbonate will deprotonate the carboxylic acid and will not react at all with the organic base, the amine. So when the carboxylic acid is deprotonated, it will be this sodium salt of the carboxylic acid, which is soluble in water because it's ionic. The amine, as I mentioned a second ago, will stay completely intact because it will not interact with this base because it is itself a base. However, I will get traces of water because I added aqueous, sodium bicarbonate, in the liquid-liquid extraction. So now I'm going to focus on this side. If I want to get my carboxylic acid salt back, I need to add an acid. And if I add 6 molar HCl, as mentioned before, this molecule is unlikely to be soluble in water, so it should precipitate out as a solid when I add the hydrochloric acid. My byproducts will be NaCl and water. In the case of the other side, where I have the organic base, the amine, dissolved in the ether layer, I want to add anhydrous sodium sulfate in order to get rid of traces of water. I'll get the solid sodium sulfate .xH2O, and in my ether, I'll have my organic base or my amine. Then I want to evaporate the ether. I should get my solid amine back, and ether will come off as a gas. So this is a good way to separate these two molecules. For the mechanism, I'm going to do the same thing where I'm going to focus on each step individually as written. So first, it says the major product may be elimination. Focus on the substitution product of the R isomer. So in this case, I'm forced to focus on the substitution product. So in the first step here, we see this methoxide here deprotonating the molecule here. Now, even if this was an elimination, which I'm specifically told not to focus on, this is not the proton that would be eliminated, right? You have to eliminate a proton over here. So this proton is not going to come off when the addition of methoxide. So step 1 is fundamentally incorrect. In the second step, we do have a plus charge here, and we have methanol acting as a nucleophile. This is theoretically possible, right? If you had a carbocation here, you could have methanol acting as a nucleophile and attacking here. However, if it did, you'd have 4 bonded carbon at this position, okay, and the bromine wouldn't have any need to come off. so that is incorrect. In the last step, one glaring thing is somehow we had this attached over here, and now the carbon is attached, and now we have 5 bonded carbon. This carbon is bonded to this carbon, 3 hydrogens and an OH. You can't have 5 bonded carbon, so that's clearly wrong. However, if we ignore that, if we look at this carbocation here, and then we have bromide acting as a nucleophile, theoretically, this could actually occur. Again, ignoring the 5 bonded carbon. So again, commentary, there's a ton of mistakes here. I'm focusing in on one mistake in each step, as to not confuse the issue and to try and make it hopefully followable, I don't know, by you, the audience. Okay, now for the correct mechanism. So again, I'm told to focus on the substitution product of the R isomer. So here we have methoxide, which is a strong nucleophile, coming in and attacking this carbon. This leads to the transition state where the methoxide is coming in and kicking out the bromide on the other side. Note that this is a transition state. It's not something that is isolated in the mechanism. Then after the transition state, we end up with basically a backside attack because methoxide comes in on this side and bromide goes out on this side. What we end up with is an inversion of the stereochemistry, or ultimately the S isomer. Notice that I have just written these as R's instead of my whole molecule in order to, not make it more clear what is going on. Now, if you want to use your whole molecule, of course, that is fine as well. So that has been the organic chemistry molecule portfolio project presentation example. Okay, it's a relatively quick example with a little bit of commentary in there, and I hope you found it helpful. Please note that you're not expected to do it exactly like I did it. You're not expected to focus on the same things that I did, but it's just to give you an example so you have an idea of how the project will go. I hope you've enjoyed the course up to this point, and I hope you've gotten something out of doing this molecule project. I know it was a lot of work. We tried to help you, spread that work out. So thank you very much for taking the course, and I really do hope you enjoyed it.